Savle, Assistant Professor from the Department of Aeronautical Engineering, heartily welcome you all for the third phase of FDP, Day 2, second session. As it's a post-lunch, I request all the participants to be enthusiastic as today's afternoon session speaker is filled with true enthusiasm and we really have a great session. It's really honored to speak a few words about Dr. Manas Das, sir. Dr. Manas Das is an associate professor in the Department of Mechanical Engineering from IIT Guwahati. He received his bachelor's degree from Production Engineering Department, Jadavpur University. He completed his master's and PhD degree from the Mechanical Engineering Department, IIT Kanpur. His research areas include advanced finishing and nano finishing processes, advanced machining processes, and micro machining processes. He published more than 33 papers in reputed international journals and published more than 43 conference papers. 4 research scholars have received a PhD degree under his supervision. Presently, he is supervising 8 PhD students in the broad areas of manufacturing. I will hand over today's session to Dr. Manas Das sir to carry forward with a good introduction note. Thank you, sir. Over to Manas Das sir.
Okay, thank you, Professor Alka Saule, Professor at Department of Aeronautical Engineering, MLR College of Engineering, for giving a nice introduction. Also respected Professor K. Srinivas Rao, Principal MLR College of Engineering, and then HOD Department of Aeronautical Engineering, Professor Satyanarayan Gupta, and Professor Sweta Bala, Associate Professor, Department of Aeronautical Engineering, who is the coordinator of this FDP. So a good afternoon to all of you, all the participants and all the faculty members. So I'm going to start my talk on this. Actually, this is basically on magnetoroidal finishing process. So this is actually this is a very smart finishing process, which is mostly actually used in aerospace industries and defense industries. So I shall discuss each and every corner of this process so that many of you may be working in the different research areas. So this also you may think of actually to start your research. So whatever we have developed till now, we shall discuss. Okay, so it is. So I'm going to share my screen now. Madam, is it visible? The screen is visible?
Yes, sir. We can view your screen.
Okay, so I'm going to talk about this magnetic field assisted finishing of aerospace materials using smart magnetological fluid. So also few materials we have considered that is not actually in aerospace material, but few materials we have considered they are actually aerospace materials. So to start with my talk, actually this is my outline of my presentation. So we shall discuss, as I told, actually I shall talk about this. This is the smart polishing method. So it is called actually magnetological finishing process. Okay, so there are different varieties are there, hybrid, different hybridization has been done. So I shall discuss each and every setups, all different kinds of setup which are available all over the world. So also the development of this setup, how it is developed. So mostly this finishing process, which is it is utilized. It started actually in USA by a senior researcher who is called actually Gordon SK. So he developed this one. Then he developed one lab there in University of Rochester. So they are developed machine which is called actually QED technology. So they have developed one startup company there, QED Technology. Now it is a very big full-fledged company, and they are selling this kind of machines all over the world. But unfortunately, our BRC and DRDO, these people, they are trying a lot actually to get one of the machine here. because this is the only process for polishing of these lenses and mirrors. So these lenses and mirrors, these are actually utilized in different actually missile technologies they use. So these are basically very high precision lenses, which are which is used in defense industries. So, unfortunately, we could not get one of the machines. Uh, uh, this work actually started at IIT Kanpur during my PhD days there at IIT Kanpur. So I shall discuss actually some of the work I did there and some of the work we did there at IIT Kanpur. Then after that, actually, after joining here at IIT Guwahati, many things actually, many different kinds of setups we have developed. We are further, we have continued in this area. So different kinds of setup we shall discuss how the fluids actually is made, how it is actually synthesized, so that you can also make in your own fluid, and some experimental results we shall show, and some simulation results also. If time permits, then I shall show. Okay. So first of all, we have to see that actually why. Okay. So before starting my lecture, I am going to tell what are the things we are doing in our lab. So this is the different setup we have developed in our lab at IIT Guwahati Precision Manufacturing Lab. First left hand, you can see here, this is the 5-axis, sorry, it is a 4-axis CNC machine. So initially we started with 4-axis CNC machine. So this is the actually knee joint here. So this knee joint, it is made of titanium alloy of grade 5. So otherwise you can use cobalt chromium alloy also. We can use so other metals are also used for this knee joint, but here we have used actually titanium alloy also it is used. This is the finishing process, magnetic field assist finishing process we have developed here. So we shall discuss later actually in entire details of this finishing process. After that, this is the plasma polishing experimental setup here we have developed at our lab. So we have a collaboration with ISRO Trivandrum. They have one unit. They are actually in IISU, ISRO Inertial System Unit. So they develop actually different kinds of sensors there. So this is actually a first figure you can see. This is the hemispherical gyro. They call it actually HRG shell. Okay, so this is around 10 millimeter diameter. You can see, and 1 millimeter thickness, and it is made of quartz basically. This one small one, it is used for gyro there. For interplanetary satellite, it will be placed. And as it is a brittle material, you know, this quartz is a brittle material. So this quartz has to be actually they manufacture it by using a 5-axis CNC machine, vibration assisted 5-axis CNC machine. All of us know that for machining of this brittle material, we have to do the machining in the ductile resin. So that's why actually this vibration is required, and they have given actually very small depth of cut with high nose radius. And after that, as it is a brittle material here, so there is a cracks, lots of cracks are generated. Very means they have taken a huge precaution so that the cracks can be as less as possible. So because of these cracks and because of this machining of this quartz, so you can see here actually lots of defects are there at the entire surface, and so these lots of defects, these cracks, it is actually up to 10 to 15 micron at the depth. So that up to 10 to 15 micron you have to remove by using a certain process, certain finishing process. After that, it can be polished. Means after that, it can be used as a sensory device. Uh, so this is the after finishing. Still, you can see lots of defects are there. So still this work is going on here. And this is another one, this laser gyro. They have a laser gyro. So this kind of prism they are using, that laser gyro. And still they are not using for in the satellite. So they are using this laser gyro, using this prism for launch vehicle. So above all, actually, you can see this is the setup here. So many components are there. So it is very means pressure. It is used at very small pressure they use. This is the plasma chamber here, right hand side figure. So this is the plasma polishing setup. So it is a medium pressure plasma. Right hand side, you can see another finishing process, which is called magnetorheological abrasive finishing process. So this it is a very versatile process. I shall discuss in detail. So that's why I'm not discussing now. So at the bottom row, you can see first setup is magnetorheological finishing setup. So we have actually mimicked one of the setup which is available at QD Technologies. So we try to develop that setup here in our lab, and I shall discuss in details this setup, this MRF setup. After that, this is the micro ECM setup, electrochemical machining. All of you know, those who are working in the area of actually manufacturing area. So this is the micro ECM setup, and we are working in the small domain, in the micron domain. So this is the setup here we have developed. So micron domain here, and so this is the excited view of the tool. So electrodes. Yeah. So other than that, we have developed one micro ATM setup also in our lab, and many more setups, small setup we have developed. So these are the most recent developed setup which we are working in our lab. Okay, so before starting off this actually this process, I'm going to explain actually why this kind of advanced finishing process are required. So normal conventional finishing process, you know, milling, this grinding, honing, lapping. So in all the cases, you know, this in grinding process, actually these abrasive particles are bonded together. There are different kinds of bonding materials, solenoid bond, Shelock bond. So these abrasive particles are bonded together. And whatever this external periphery, whatever these abrasive particles, those which are taking part in the material involved, they are called actually active abrasive particles. So these abrasive particles, they rotate with a fixed path. Suppose if there is a complex contour, whatever I have shown earlier, that actually suppose there is a knee joint is there. So you can see it is a free-form surface, and this kind of surface cannot be expressed by any analytical equation. So some polynomial equations are required. So you can see there are so many surfaces are there. So these surfaces are stitched together to give this kind of means total entire surface. So for finishing of this kind of complex contour of free-form surfaces, it is very difficult by conventional finishing processes. So first one is the complex geometrical shapes of nowadays, whatever these engineering components are there. And also in grinding process, you know that whatever this controlling forces, it is very limited. Okay, so we want to control the finishing forces externally during means in situ controlling of the finishing process or abrasive forces is required, which is not possible in normal grinding, honing, or lapping. And in lapping process, actually, you know that there is a polyethylene pad. If there is a complex surface is there, so in that case, actually on that polyethylene pad, so these abrasive particles are sprinkled, and one experienced labor or technical technician or technical person who does this finishing by moving his hands over the surface, and in between there is a polyethylene pad is there. So suppose if you want to get in for finishing everywhere on the knee joint, what I have shown there, he or she has to know that where you have to give pressure. Okay, so it depends, entire thing actually interpolishing depends on the uh, skill of the means that technical person. So whenever that person actually leaves, then the company faces lots of problems. So we need to automate all this process, this kind of process. We need to automate all these processes. So that's why actually we need to have actually precise control of this finishing process is required. And also I told like these lenses which are used in defense industries, they are the surface finish over the component on the lenses, actually it is in the angstrom level. The surface finish requirement, it is in the angstrom level. So normal finishing process is very difficult. Normal finishing processes are very difficult to polish. This kind of what conventional finishing process is very difficult to polish for this kind of components. So these are the requirements of advanced finishing processes. Okay. So now these are the different components I'm going to show here. So here first one you can see that actually investment cast milled parts. So it is made of actually casting process. So lots of bars are there. So here you can see lots of bars over there. Actually it is not polished at all. So this kind of complex surface, it is very difficult by conventional finishing process. So you have to go for some advanced finishing process. Okay. Second one, this the airfoil profile. Okay, so the first one is the polished one. This is the unfinished one. So you can see unfinished one. So it is too much rough there. Okay, after finishing it, that has become this kind of mirror-like finish. It is got. So after that, this is the cast. Uh, it is the cast aluminum component here. Okay, so automotive turbo component. So and after that, this is the bend tube here. You can see. So this kind of bend tube, it is used in medical industries for flowing very pure gas. And if the internal surface of this kind of bend tube, if there is some kind of actually rust is there, then it mixes with the pure gas. So that's why before finishing, before using this kind of tubes, so you have to polish it very efficiently. And there are certain medical components you can see right hand side, this kind of medical components. And after that, this kind of automotive gears. So if it is not polished properly, so there are lots of bars will be there. And then there will be backlash here, all these things. Nowadays, very small gears are used in different components. Okay, so in earlier days, actually this watch, whatever watches are there, actually precision watches, they are small gears are used. Um, these small gears, very miniature gears, they are fabricated by using YDDM process. So we know that actually in YDDM process there is a recast layers are there. This kind of gears has to be polished before using in a real component. And now after that, this kind of actually hard valves you can see here, automotive components here. Now this is the exhaust manifold. You can see there are two manifold which is connected to pipes which is connected. And these kind of pipes, they are welded together, and at the welded junction, you can see lots of heat affected zone will be there. Then again, this kind of recast layer will be there. Okay, so the slugs will be there. So this kind of components actually it has to be polished before using, because if it is not polished properly, there will be restriction, flow restriction over the surface where actually there is kind of joints are there. Now this kind of high pressure holes in the diesel injector nozzle. So internal surface you can see these are the holes are there. This at the internal surface you can see these holes where this connected to the bigger actually hollow holes. So there it's this surface has to be actually rounded here. So it is called actually radiusing of the hole here at this point, so that actually there will be a smooth flow of fluid while discharging through the nozzle. Okay, so these are the different components. Another components I'm going to show here. So this is the in our knee joint basically. So here this is the femoral component. This is the tibial part. In between actually there is a polyethylene component is there. Uh, uh, so uh, this is actually made of uh, uh, high molecular weight polyethylene. Okay, ultra high molecular weight polyethylene. So this part actually over time it damages and then it is replaced. This metal actually it is made of you can use titanium alloy, you can use actually cobalt chromium alloy. So this femoral component, it is as it is constantly it is touching to the polyethylene component. So if small amount of undulations, if it remains there, so if it is not polished properly, So what happens actually over time, these there will be more friction will be there, and whatever these debris particles. Okay, so whatever these debris particles, they will come into contact in between, and then there will be three body, two body abrasions will be there, and these debris particles over time they will increase this friction and wear and tear, more wear and tear, and then ultimately there will be total failure of this membrane component, and the person wearing this one actually feels lots of pain in that case. So this kind of components you cannot frequently change also. So we need for a longer life of this kind of components, we need actually nano level finishing at this external surfaces, so that actually it can be used for a longer time. So after finishing this component, femoral component, we can see it is a so it is actually this mirror finish, this kind of, so here surface finish, it is in the nanometer range, and we need actually surface finish in the uniform surface finish. Everywhere surface finish should be same. So in entire components, everywhere surface finish should be same, and that surface finish should be in the nanometer range. So with this introduction, you understood actually how why this kind of nano finishing, why so this is the requirement of nano finishing process. Okay, so now I'm going to our different nano level finishing, nano finishing experimental setup. So this kind of these are the different advanced finishing process actually which is available. So the first one is called actually abrasive flow finishing. Second one is the magnetoreological finishing. So we shall discuss one by one how what are the different advanced finishing process which are uh, uh, available in the literature. Okay, so first one I told this is the abrasive flow finishing process here. There are two pistons you can see. So right hand side you can see here actually is the top piston, is the bottom piston here. In between these two piston, so this is the polishing fluid cylinder. This is the bottom polishing fluid cylinder. So there are two cylinders. These two cylinders they are filled with actually one medium. So this AFM medium. So this medium it is called actually viscoelastic medium. So there are one hydraulic pump which is used actually to give this kind of reciprocating motion. So this while giving this kind of reciprocating motion, so this means these two pistons they reciprocate together. So this top piston when it goes down, then at that time this bottom piston also it goes down. So these two pistons there is a reciprocating motion. This kind of reciprocating motion is given. So while giving this kind of motions here, actually this viscoelastic media, it flows through the this restricted area where you are giving your workpiece. So in this case, they kept for explanation, they kept one cylindrical workpiece here. Instead of cylindrical workpiece, you can keep your actually this. You can keep your this femoral component also. You can keep it here. So only thing is that actually you have to design this finishing zone to accommodate your workpiece, and you have to flow the media. You have to make sure that media is restricted to flow over the surface. Media is restricted, so there is a restricted movement of this media over the surface of this workpiece. So like that, this kind of restricted motion is given there. Okay, so like that, this kind of restricted motion is given, and it is flown through this restricted zone here. So this process is a versatile process. You can see here any internal external surface can be polished by this process. But one thing is that in this case certain limitations are there. Okay, so although it is a versatile process, surface finish in the range of nanometer. Okay, so one limitation is that actually this viscoelastic media, which is developed by Extrudon Corporation, so they have a monopoly. So no other parties are there who develops this kind of media. And this media, it is a very means beautiful media, very smart media. This media actually it takes the shape. Means if you keep it in your hand, it takes the shape of your hand. Means it can take the shape of the any of the workpiece, so any complex contour of the of the workpiece. So any kind of complex surfaces can be polished. Any kind of complex surfaces can be polished by this abrasive floor machining experimental setup. Okay. So uh, so but one limitation is that here, so this viscoelastic media, which extrude honor actually prepares, it has a it is very costly. Basically, it is 1 kg. It is around 5 lakhs. And second limitation is that this media rheology actually, rheology means actually rheology is very important here because you know this in grinding mill, these abrasive particles actually it is bonded into that bonding material. When there is a huge force comes, in that case, actually these abrasive particles actually removed from the bonding material. Okay, overcoming this bonding material and new abrasive particles comes there. But while doing normal finishing process by grinding process, this bonding material should hold the abrasive particles. Okay, for doing the surface, for removing the surface undulations from the workpiece surface. So here this viscoelastic media does the same thing. Its rheology is defined in such a way that this media can hold the abrasive particles while indenting into the workpiece surface. So this media actually, if you order this media, they will ask actually which workpiece material you are going to polish. Accordingly, they will give their own media, but it has been found that suppose same media cannot be used for different kinds of materials. Like you are finishing brass and you are finishing stainless steel and you are finishing titanium. For three different cases, three different media is required. Okay, so same media cannot be used for polishing different kinds of materials. And also this process, external control of the finishing forces or for precision polishing, actually external control of the finishing process is required. So in this case, actually, we cannot control the finishing forces externally. Okay, so that is the limitation of this FM process. And now second process is called actually a magnetoreological finishing. So already I told it is developed by Center for Optics Manufacturing, Rochester University. And after that, they have developed their actual startup company, which is called QD Technologies. So here, media stiffness, it is a function of magnetic field. Okay, so I'm going to explain how this works here. Okay, so in this figure, you can see here this MRF process. This MRF process is consists of actually some base media. You can take oil-based media or you can take water-based media. Any of this media you can consider. But this base media actually it consists of these CIP particles. So these ferromagnetic particles, these are called actually CIP carbon particles. These CIP particles are connected together along the magnetic lines of force. So here you can see this is the North Pole and this is the South Pole here. And along the magnetic lines of force, these CIP particles are actually making this kind of chains. And now this MR fluid, it consists of abrasive particles also. So here you can see these bigger size particles for understanding actually these abrasive particles are made bigger. So these bigger size abrasive particles, they are bonded together in between these CIP chains. Okay, so if you don't have these abrasive particles are non-magnetic particles, only these CIP particles are ferromagnetic particles. So these iron CIP particles along it will make chains along the magnetic lines of force, and for movement of flow or for the fluid flow. Okay, so you have to apply pressure which should be greater than the yield stress of this fluid. So when applied pressure is greater than yield stress of this fluid, then only this fluid started moving. Okay, so what happens in that case? Whatever these chain structures are there, say particle chain structures are there, they breaks. When chain structure and ferromagnetic particles this chain structure breaks, that time basically uh, actually this fluid flows. So okay, so for the flow of media, you need to break the chains. So that's why means when your applied pressure is later than this yield stress of this fluid, then this fluid does not flow. Whenever this applied pressure is greater than yield stress of this fluid, then the fluid start flowing, and there is a breakage of this chains, and due to that actually this chain started flowing. And also these abrasive particles are these iron particles or ferromagnetic particles, they don't take part into the material removal. Only the abrasive particles are taking part into the material removal. But in this case also, like in grinding operation, I told that actually this bonding material, they give bonding strength to the abrasive particles. In this case, who is the bonding material? So the CIP chains, which is these abrasive particles are embedded in between the CIP chains. So because of this surrounding CIP chains, by the active surrounding the abrasive particles, these abrasive particles get bonding strength by the surrounding CIP chains, and it is indented into the workpiece surface. Okay, so these abrasive particles are taking part into the material removal, but these spherical CIP particles, they are actual soft iron particles. They are 99.9% pure iron particles. They don't take part into the material removal, basically. Okay, so coming to this figure here, so this is the media. You can see MR polishing media, which is flowing from left to right. Okay, and this workpiece, which is this workpiece here, you can see convex shape. That is a convex shape. This lens. Sorry. Sorry for the interruption. So this convex shape lens here, this lens actually it is attached to the head of a workpiece holder. So this is the workpiece holder basically. In front of that actually this convex shape lens which is attached here. Now this workpiece, it is rotating about its axis. There is a rotation about its axis, and also there is a dwelling motion is there. So you can see here there is a dwelling motion. So as the workpiece is rotated, so there is a small spot will be there. So this MR fluid, it is flowing from to left to right, and magnetic field is applied in the finishing zone only. So in this zone only magnetic field is applied, and in this zone only this finishing forces generates, and it becomes stiff in this zone only. Okay, now this kind of dwelling motion is given, so that actually this, if you give this kind of dwelling motion, you know at one spot how much time is required to polish one spot. So if you give this kind of dwelling motion, in that case entire surface of the workpiece can be polished. Okay, now this is another setup here. So here you can see this disc is there. So this disc is rotating about this axis. This disc is rotating here. And again, there is a workpiece holder. So this workpiece holder, it is rotating also in its axis. So there are two opposing rotations is there. One is the counterclockwise, this disc rotation, and clockwise, this workpiece rotation. And magnetic field you can apply. So here you can see north and south pole of this magnet here. So that's why they are applying magnetic field in this zone only. So in this finishing zone here, so in this finishing zone, this MR fluid will become stiff here in this zone. Okay. So this workpiece is actually dipped into this finishing zone, into the MR polishing media. And as the magnetic field is applied, this CIP will form this kind of chains, and it will become stiff. This polishing media becomes stiff. It becomes actually solid-like behavior. Okay, so after that, actually, this workpiece is actually it is dipped into the polishing media, and with this two circular motion and dwelling motion, the entire surface of the workpiece is actually polished. So this is one of the setup for this macroradiological finishing. I already told here this setup, another setup. This one I have shown actually for discussing the how this MR polishing media actually works. Now, here you can see in this zone where you are applying magnetic field, these CFP particles are forming chains here only in this zone. And without application of this magnetic field here, where you are not applying any magnetic field, so this MR fluid, it is a homogeneously distributed. It behaves as a Newtonian fluid. But when it comes to the magnetic field zone, it behaves as a non-Newtonian fluid. Now, this working principle of this magnetological finishing. So this is the setup. Actually, it is developed by Podolsky et al. At Center for Optics Manufacturing, Rochester University, USA. Later, actually, whatever this QD technologies they developed, these commercial machines like this one. So here you can see there is a disc is there. So in the schematic diagram also you can see there is a disc. This disc actually top surface it is part of a sphere here. So it is made like a part of sphere because whatever this MR fluid which is moving over the surface, whatever this MR fluid which is moving over the surface of the basically it is called actually drum. So what the surface of this drum, whatever this MR fluid is coming here, so magnetic field is applied here and it will become stiff in this zone only. And the spherical surface is given to make a small spot diameter. And after that, using this dueling motion, entire surface of the workpiece is actually polished. So if there is a very small spot diameter, that intricate details you can easily polish very precisely. The intricate details you can polish very precisely. So that schematic diagram we can see here, there is a drum. So external surface, it is spherical here. So there is a delivery nozzle. Through this delivery nozzle, MR fluid is delivered over the surface of this drum. Now this drum is rotating with a certain RPM, and there is a suction nozzle here. So whatever is MR fluid which is delivered through this delivery nozzle, it comes back to the suction nozzle, and there is a delivery pump, and there is a suction pump is there. Through this nozzle, it comes to this pump, and then there is a MR fluid conditioner is there. So it is collected at the MR fluid conditioner. Okay, so MR fluid container here it collected, so and then its yield stress, viscosity, temperature, all these properties actually it is maintained here at this MR fluid container. Now, why this MR fluid conditioning is required? Because this fluid it contains base media. If you are polishing quartz, glass, or mirror, uh, uh, so here actually this whatever this MR fluid media is there, actually it requires uh, monitoring of its yield stress and viscosity. As there is a friction in this zone and this fluid comes into the atmosphere, so it is open here. Then because of friction and due to the environmental effects, so there may be means so this MR fluid viscosity actually changes because of this temperature gradient here in this zone in the open air here in the atmosphere. Okay, so this whatever this water molecules it evaporates and its viscosity and yield stress changes. Also, you know that with the temperature, actually this viscosity and yield stress of this media actually will be different. It changes basically. So that's why this MR fluid conditioning is required. So this kind of peristaltic pump is required actually for delivery and suction of this MR fluid there. And here you can see this is the North Pole and South Pole. They are made in such a way that this MR fluid it would be they made it in such a way that this MR fluid will be this magnetic field is actually delivered in this zone only at this point where you have kept your workpiece there. Okay, so that's why their designing of this electromagnet core material is very important. So they have made in such a way that this magnetic field is concentrated at the zone where you are doing the finishing operations. So this setup actually we can try in our own actually in our lab. So I have developed some setups we have developed, which I'll discuss later. Okay. Now, again, actually, this mechanism of finishing. So here, this dotted line actually it is shown. It is tilting. There is a tilting motion is there. So which is called actually dwelling motion in case of this magnetological finishing process. Then this magnetic, due to this magnetic field, actually this in this zone, MR fluid become very stiff here. It behaves like a solid-like behavior. So this MR fluid, it is moving from right hand side to the left hand side here, and it is sheared in this zone, and it makes a very small spot here. Okay, so after that, actually, this spot moves to the entire surface of the workpiece as you are giving the dwelling motion there. Okay, so here in this zone where this small spot is generated, the finishing actually it is conducted and is carried out due to the shearing motion of the MR fluid. So because of the shearing motion of this MR fluid, this finishing actually occurs. In this zone here, this finishing occurs due to the shearing of this actually for the media, finishing media. And this small portion of this finishing support occurs, their finishing occurs, and after that it is given this kind of dwelling motion. So entire surface of the workpiece actually it is polished. Okay, so like that, this kind of lens is actually polished by this microbiological finishing process. So there is one equation which is used for calculating this material removal rate in case of this metallurgical finishing process. V is the pressure, which is applied pressure there, and use the relative velocity in between this MRP driven or polishing media and the workpiece surface. So what is the relative velocity? It is comes into the U actually, relative velocity between MRP driven and workpiece. And K is the actual empirical coefficient. It depends on the process which combines surface chemistry, ablation effects, and post-polisher contact. Okay, so it depends actually whatever these CIP particles, whatever this abrasive particle concentration you are using into the media. So everything comes under actually K. So it is an approximate equation, but still it is used for calculating the finishing metal removal rate in case of metallurgical finishing process. So all these two figures already I have shown. These are the actually earlier development of Rochester Center for Optics Manufacturing, University of Rochester, USA. But this key feature I'm telling here, it can polish flat surfaces, external surfaces, spherical, aspherical lenses, convex, concave, what kind of lenses are there. But it cannot finish the limitation is that it cannot finish actually this internal surface or very complex contour, it cannot polish. Also say here this surface finish, you got actually the angstrom range, nanometer angstrom range, and it is a deterministic finishing. Surface finish means external surfaces can be controlled to control the finishing mechanism. And this limitation is that actually this is used for only for flat workpieces, for polishing of flat workpieces, and it is not suitable for polishing complex contours and for polishing of internal surface. So now we know that actually FM process, which is a very versatile process, any kind of complex contour, it can be polished. It can be used for polishing. But this AFM process is their media. There is a restriction. There is a media cannot same media cannot be polished for polishing different varieties of workpiece material. But in case of microbiological finishing process, you see that actually whatever is MR fluid, MR polishing fluid is there. Same fluid can be used for polishing thousands of different types of workpieces of different hardness, different physical properties. Okay, so as the these finishing forces can be controlled in case of metallurgical finishing process. Okay, so these are the advantages of both the process. So that's why by combining, okay, so this is the setup actually we have developed in our lab. So here you can see there is a polishing disc actually which rotates about a shaft Here there is a belt drive is there. Through this belt drive, there is a BLDC motor or brushless DC motor, and there is a SMPS is there, and it is actually it can be rotated. It can be rotated by using this BLDC motor here through this chain drive. Okay, so here we are using actually permanent magnet instead of electromagnet. We are using permanent magnet. So we are using only this prototype. So that's why in original case, as the workpiece is very big. So in that case, this process very small movement of workpiece is very difficult. So that's why what people have, means what we have done actually, we are using permanent magnet here. So here NDFEB permanent magnet we are using. So this top surface, it is a part of sphere here, you can see. And there is a two stepper motors are there. These two stepper motors are used for XY movement of this table. And Z axis movement, it is done by a manual lag. So that is a manually you can change the workpiece in between the gap between this fluid media and the workpiece. And this is the workpiece holder here. So only top flat surfaces can be polished by this process. Okay, so that's why. So I think you have understood actually how this setup works. So there is a controller is there for controlling these two stepper motor. Through Arduino, actually we are controlling. So entire experimental setup is developed in our lab. Okay, so now coming to that actually how this MRF process actually is developed. So by taking advantages of a FM process, which is actually very versatile process, and also by taking advantage of this, by taking advantage of this methodological finishing, where these finishing forces can be controlled by external means. Okay, so by taking these two advantages and joining the combining this FM and a methodological finishing process, we have developed one process which is called methodological finishing process. Okay, so this process also, it is a versatile process, as it is FM, existing FM process is actually modified here. In FM process, what we did actually, whatever this polishing media which we are using, that polishing media is replaced with the MR fluid, meteorological polishing fluid basically. So this process is called actually meteorological finishing process. Here you can see this actually experimental setup here. Now in this experimental setup, this right hand side here, you can see this is the hydraulic unit here. So this hydraulic unit we have considered 0 to 100 bar. It has a three-phase motor here, and there is a direction control valve here. So here there is a direction control valve, because we are going to give this as a reciprocating motion. So how this one works, I am going to show here. So this is the top meteorological polishing fluid cylinder. This is the bottom meteorological polishing fluid cylinder, and this is the hydraulic cylinder here. This is another hydraulic cylinder. So here one piston will be there here in this point, one piston will be there, and another piston will be there at the top meteorological polishing fluid cylinder. And these two pistons actually they are connected by a connecting rod. So for the bottom case also, in this bottom meteorological polishing fluid cylinder, it also consists of actually MR fluid. Here one setup in one piston is there, and in the hydraulic unit one piston is there. So these two pistons they are connected by a connecting rod. And now while polishing actually this hydraulic fluid, actually it comes through this cylinder, and it comes to the actually this top MRPF cylinder there. So with pressure, so this hydraulic oil, it is coming here and giving pressure to this piston here. So this piston and this piston, they are connected. If you give pressure to this one, then it will be placed here. Okay. after that, what happened? So whatever this media just below the hydraulic coil, just below this actually piston here, it comes back to this hydraulic unit here. And then there is a limit switch here. It is placed as this at this point. When this limit switch touches, then when there is a this piston actually goes to the bottom dead center. In that case, that limit switch actually activates, and if the limit switch activates, it gives current signal to this hydraulic unit, and there is a direction control valve which changes the direction, and then initially if it is coming to the bottom dead center, then again it goes back to the top dead center. So like that actually this pulsing media works. This magnetological finishing media works. So this is the finishing zone. You can see here, this is the finishing zone. This is the north and south pole of this electromagnet, and this is the core material. So these are the two core materials here. There is a north pole and south pole of this core material here. So in this case, actually, this diameter gap between these two core material is 30 millimeter, and we are using actually electromagnet. So electromagnet, this advantage is that same electromagnet can be used for polishing different kinds of the material. So these finishing forces can be controlled in case of this electromagnet. But in case of permanent magnet, which we have used permanent magnet, so in that case, the magnetic field cannot be changed. Okay, so for polishing different kinds of material, you have to use different kinds of permanent magnet. Okay. So with this actually introduction, so I'm going to show here this magnetoroyological experimental setup here. So this the just I shall take 1 minute. Uh, Sorry for the disruption. Okay, so this is the experimental setup here which we are using. Okay, here you can see this is the two coils, electromagnet coil here, and this is the core material here. Okay, so this is the DC power supply here. Using DC power supply, you are energizing these two coils of that electromagnet, and we can change the current here from this DC power supply to change the magnetic field, which is provided by this electromagnet. Okay, so through this hydraulic unit right inside, through this hydraulic unit, we can give reciprocating motion. So here this is called, okay, this hydraulic unit here, limit switches are there, which is attached. One and limit switch is here, another limit switch, it is attached here. You can see using these two limit switches. So when it is coming down, this piston is coming down, then at the bottom its center, bottom dead center, actually this limit switch actually energized, and there is a direction control valve of this hydraulic unit, and then this flow of whatever this hydraulic oil, it comes through another channel. So initially it comes from this side through a pipe, and then while returning it comes from this side. So there are two limit switches are there to change the direction, to energize this direction control valve, and like that actually fluid flow actually changes. So like that we can give this kind of reciprocating motion here. Okay. Uh, so you can see here actually what about this. Uh, so these are the different kinds of actually workpiece fixture which we are using. Okay, so this kind of straight flat workpieces we are polishing. So it is fixed at the internal surface of the cylinder, stainless steel cylinder here. And these are the silicon nitride workpieces which we have polished. This is the entry and exit device, similar entry and exit device to the finishing zone, and which connects to the actually MR polishing fluid media cylinder basically. Okay, so by using this kind of arrangement, actually this media is actually flown through the finishing zone, and we can do the polishing action actually. Okay. So this is the electromagnet here. It is called S-type electromagnet. Okay, so this is the core material of this S-type electromagnet here. So this one actually is the core material here, and then this is the coil. So this is the coil one, and this is the coil two. And in between this two core material, there is a gap of, you can see here, 30 millimeter gap here. The length of this electromagnet coil, individual coil, it is 80 millimeter. And then this diameter of this actual electromagnet coil, which is 160 millimeter here, and then diameter of this core material, which is actually 50 millimeter here. So there are two coils, you can see there are two coils. So here north pole or south pole, depending on the direction of the current. So two opposite pole will be generated here. So this is the exact view of this electromagnet. So here it is designed using Maxwell. One software is there. Actually now ANSYS has purchased that software. So earlier it was Ansoft Maxwell, now it is ANSYS Maxwell. If you purchase MCL, if you have license version, you will get this Maxwell there, and you can design this kind of electromagnet. And this electromagnet, you can see individual coil. It consists of actually 2000 turns of wire. We have taken actually square wire. Okay, so the square wire actually it is important because it increases the packing factor, and outside there is a copper. Uh, this copper tube is actually escaped for better heat transfer. Okay, so because it prolonged use, this coil actually gets heated up. So that's why actually this kind of copper, this tube is used, and where chilled water is delivered through this copper coil or copper tube. Okay, so this is the electromagnet you can see. Now, how to develop this MR polishing media? In this polishing media, you can, I already told that the base media is there. So this base media, it is called continuous phase. So it consists of either water-based media, or it is a means mineral oil-based media. Water-based media actually generally uses deionized water, and oil-based media generally uses actually the silicon oil or paraffin oil-based media they uses. Okay, so there is a then actually there is some additives also used. These additives because actually this base media, this base media actually this water-based media it is used for polishing lenses, mirror, glasses, and oil-based media is used for polishing of mostly this polishing of these metals. Our experimental setup, whatever I have shown there, actually mostly they are mild steel and cast iron. This cylinder, MR cylinder, it is made of cast iron. So there is a problem of rusting, and if you are using this water-based media, then over time you will see that actually there will be it will be damaged. So rusting will be there. So that's why we have used oil-based media. Okay, so now it is mixed with actually iron particles, CIP particles. So these are actually ferromagnetary particles. 99.99% pure. These iron particles, so its density is 7.81 gram per centimeter cube. So as the density of this iron particles is higher than this base media, so there is a problem of sedimentation of this iron ferromagnetic CIP particles. Okay, so to resist the sedimentation, what we did, we use certain kind of additives there. So we have used epithelials as the additives. So by adding these additives, what happens? Whatever the sedimentation problem, it is actually reduced. And also we have used one kind of surfactants, which is called actually oleic acid. Oleic acid used as a surfactant there. So what happens that there is a agglomeration of these polishing ferromagnetic particles are there. So what happens, agglomeration means actually when you are applying magnetic field, these CIP particles will form chain and will be magnetized there. And all CIP particles will come together and then they will make a bigger chunk of CIP particles. So when these CIP particles are agglomerated, then we need actually micron size CIP particles, iron particles. But when CIP particles, because of this magnetic field, when it's agglomerated, then there is a bigger chunk of particles they make. And in between, suppose there is an abrasive particles is there, then it get more bonding strength, and it will, because of this bigger size iron particles, so these abrasive particles in between it is held there, and it will remove non-uniformly from different places. So to resist, to avoid that agglomeration, actually what we did, actually oleic acid is used. The surfactant make a layer over the surface of the CIP particles, and so that actually the CIP particles cannot come together. And now by using this process and this entire thing actually, and that is a long process. So around 1 hour time it takes actually for making this base media as well as this magnetic dispersed CIP particles, which is mixed in a container using a stirrer. So we have used a stirrer. So around 1 hour time we use actually for mixing purpose. When there is a homogeneous mixing of these particles actually, is mixing is carried out, and after that actually mix abrasive particles to make it actually uh, uh, polishing media, so magnetoroidal. So after mixing these abrasive particles, it becomes a magnetoroidal polishing media, MRPM. Okay. Now, so this MRPM, it looks like this one you can see here. Okay, so without application of magnetic field, so it is kept inside a container here. So it is little bit stiff. So one more property is that actually this CFB particles, it is very pure, 99.99% pure iron particles are there. So it concentration around 30 to 50%, and particle size 10 to 30 micron particle size. And other choices are there actually, manganese zinc ferrite or nickel zinc ferrite. So other types of ferromagnetic particles also it is used. Okay, so it has a maximum saturation magnetization of 2.4 Tesla. So means if we apply up to 2.4 Tesla magnetic field, it will not get magnetized. So this one magnetic field, it will not saturate basically. So it will keep on magnetized, and then up to 2.4 Tesla, it will become at 2.4 Tesla magnetic field, it gets saturated. Okay, so uh, uh, for this oleic acid or glycerol, it is used for as a surfactants. Okay. Now these iron particles, CIP particles and abrasive particles without application of magnetic field, you can see here. So when no magnetic field is applied, you can see here it makes a homogeneous mixture here. Okay, so and these are the actually microscopic figure. So when you are applying certain magnetic field, then these CIP particles form a this kind of chains it forms, and this white color you can see these are the abrasive particles here. So these abrasive particles are held in between these CIP particle chains, and so this is the direction. Along this direction, we are giving magnetic field, and then you have to flow this media from right to left means after breaking this chains, then there will be a flow of media. Now, one beauty of this CIP particles is that carbon particles is that you can see here this hysteresis lobe. So in this hysteresis lobe, you can see here this dominant magnetization is very less. So you know that for ferromagnetic particle, if you do the actual hysteresis lobe, so there is a machine which is called vibrating sample magnetometer (VSM). So you can, in using VSM, you can study the magnetic property of this media. And then when you are applying magnetic field, so up to, so here we have used actually up to 1.75 Tesla magnetic field we have applied here. So you can see this with increasing magnetic field, it is getting magnetized. These iron particles or this MR pollution fluid get magnetized, and the saturation magnetization is around 130 EM per gram. So then when this magnetic field is released slowly, then you can see here it takes a loop, hysteresis loop here. So this portion here, this one, it is called actually the remnant magnetization. This remnant magnetization is very less in case of the CIP particles. So these CIP particles, it is manufactured by this BASF Germany. So this is one of the world-known, renowned chemical company situated in Germany, and they actually manufacture the CIP particles. So initially we got actually free of cost. They supplied for a long time free of cost, and after that now they are charging little bit. Now if you don't want to use this CIP particle from this BSF Germany, you can purchase from some other companies are there, that is called electrolytic iron powder. Okay, so the process is different but almost similar, but electrolytic iron powder, they have a size limitation, so their size is fixed, but the CIP particles, they have different grades, different sizes of iron particles, CIP particles. Okay, so this is FeCO5. This is one of the beauty of this. Okay. So this remnant magnetization is very less. So advantage is that if you demagnetize, if you remove the magnetic field, then magnetic this immediately actually this fluid will be demagnetized. If it is not demagnetized, you know that actually in our school days used to do this actually magnetize by do the magnetization by a permanent magnet on a ferromagnetic material. Then after rubbing for certain time, actually this ferromagnetic material get magnetized itself. So in this case, if this ferromagnetic particles, CFE particles gets magnetized and small amount of remnant magnetization remains there, even a small amount of remnant magnetization, then these CFE particles will agglomerate with each other and they will make a lump of this kind of small lump, different lumps will be generated by this agglomerated CFE particles. And this homogeneous mixture of this iron and abrasive particles will not be there. So non-uniform particles size distribution would be generated. So that is not expected actually while polishing. Now, some rheological characterization is required because you know this illustration viscosity of this media is very much important. The semi fluid, it behaves as a non-Newtonian fluid after application of magnetic field, and without application of magnetic field, it behaves as a Newtonian fluid basically. Now this semi fluid, it can be termed as actually like 20 CS means 20% by volume of CS grade CIP particles, and then 20 SiC means 20% by volume silicon carbide abrasive particles of 1500 is the main size here. Okay, so this we can see in this figure. So this CIP particles white color and this black color, this the abrasive particles here. So initially the CIP and abrasive particles, they are actually making this kind of homogeneous mixture. Then when you are applying certain magnetic field, when you apply certain magnetic field, the particles actually, it is basically a schematic diagram. So the CIP particles, they are forming this kind of chains along the direction of this magnetic field edge. And these abrasive particles, they are actually held in between these CIP particles. Now, when you are giving certain amount of shear here, then these iron particle chains become bent. These are inclined. So they become inclined here. Then with a very high shear rate, then what happens actually this chain structure breaks. And when you are applying a very high shear rate, then at that time actually this chain structure after breaking, then they cannot come, they cannot join together. They don't get sufficient time to join together, and then it is permanently sheared, and then this after shearing, this fluid start flowing. Okay, so it has a certain illustration viscosity which we shall discuss. Okay. So that's why actually this we have to measure the yield stresses and viscosity of this policing media. Here you can see that the capillary rheometer is used here for measuring the yield stress and viscosity. So these are the CFP particle chain because north and south pole it is just opposite to the cylinder. Inside this capillary, this MR fluid is kept here. So you have to maintain L by D ratio, means length over which you are applying magnetic field and diameter of the capillary. It should be more than 40. And this is the direction of this magnetic field, and this is the direction of this fluid flow here. So what happens actually this MR fluid, so this capillary diameter, using this capillary diameter, you can measure the yield stress and viscosity of this policing media. Okay, so at the wall of this capillary, the shear stress is SW and shear rate is actually 4Q by pi 4Q dot by pi RQ. Okay. Uh, so the shear rate and shear stress, and these are actually calculated at the wall of the cylinder. So here, so this cylinder here inside the cylinder, MR fluid actually passing, it's flowing when there is a this the cylinder of length L and a diameter 2R. And so that is a pressure gradient LP is used. Is that LP is the pressure gradient or is the radius of the cylinder here. So you have to calculate the volumetric flow rate. So Q dot is the volumetric flow rate. From this Q dot, if you can calculate the Q dot from there, for Q dot by pi r cube, you can measure the shear rate. Shear stress you can calculate from here. And if you plot this kind of thing, and you will get the yield stress and viscosity. So if you plot all these points at different shear rate, you can get this kind of line. You can get, and this one by slope will give the plastic viscosity. And if you extrapolate this one, so it will this line, so it will be touching here and divided by this 4 by 3 psi, you will get the psi yield stress of this fluid. Okay, so this kind of capillary diameter, this setup is used, and through this capillary, this MR fluid is flown. So you can see here this schematic diagram. Initially, we have used compressed air. So after that, we have used our own setup. So later, we have used our own setup for this flow of media. Okay. So this is the experimental setup we have used here. Same experimental setup. So this top MRPF cylinder is filled with MR fluid. So it is passing through this capillary tube, and we have applied certain magnetic field over there using the electromagnets and different magnetic field and different pressure. Actually, we have used a different pressure and different magnetic field. We are passing uh, this MR fluid through this capillary tube. And another one is that there is a parallel plate rheometer is there. Uh, Actually, there is a lots of disturbance. So can anyone, the organizer, can you just stop this disturbance? Sorry, actually, there is a lots of disturbances there. So it is very difficult. Organizer, could you please stop this disturbance? So this is the parallel plate rheometer. You can see there is a uh, Okay, so this is the parallel plate emitter you can see here. So there is a tool master is there and there is a bottom plate. Okay, so in between this MR fluid is kept. So this tool master, it rotates with a certain RPM, and while rotating actually it generates certain kind of shear rate. Okay, so at a certain RPM, so this shear this so can you mute some of the participants? It is lots of disturbances are coming. So these are the different models which are used. So Bingham plastic Herschel Berkeley and Cassel fluid model. These models are used actually for so these are the different models which are used actually to model this MR fluid. There are Bingham plastic Herschel Berkeley and Cassel fluid models. These three different models are there. So after doing experiment, these are the points where the shear stress and shear rate are actually identified, and then they are fitted with the three different models: Bingham plastic, Herschel Berkeley, and Cassel fluid. Okay, so we have done few experiments there. We are not going to show here. And then based on this Oscar quotient of multiple determination, we have find out what models actually fits here. So you know this actually viscosity, it is decreasing with the increasing shear rate. So this amount fluid is a shear thinning fluid. Okay. So here again we have shown here this ambient magnetation which is very less here in this case. After that actually we have done few experiment by changing pressure finishing cycle and then by changing magnetic field. Mm, So this kind of workpieces we have used, flat workpieces, and magnetic field it is varied 0 to 0.57 Tesla magnetic field. And extrusion pressure it is 3 to 4.25 megapascal and finishing cycle 0 to 100 cycles we have used. And this is the initial surface roughness profile, this is the final surface roughness profile, and this is the change in surface roughness profile here. So with the increasing magnetic field, you can see here actually this change in surface roughness increases. And here initially without any magnetic field, these abrasive particles just rotate over the surface undulations without cutting the peaks. And when you have applied certain magnetic field around 0.57 Tesla magnetic field, these abrasive particles as they are bonded here, it removes the surface undulation. So without magnetic field, it does not without magnetic field actually it does not remove the surface undulations. Okay, so then again extrusion pressure we have done certain experiment. We have seen that actually around 37.5 bar pressure actually this surface improves a lot. And then with finishing cycle also we have done many experiments. Okay, so what we have seen that initially this with finishing cycle, increasing finishing cycle, surface finish actually improves, and after that with the removal of this or whatever this uh, material, loosely held material over the workpiece surface, after that actually real surface actually comes out, which is very hard, and then with finishing cycle it removes further. Okay, so after that actually we have developed another setup which is called rotational MRF process. So in this case actually magnetic field is applied at just opposite direction, north and south pole. In other surface there is no finishing, so that's why we thought of actually rotating the magnetic field using this permanent magnet like this one. Suppose you want to polish the cylindrical workpiece or any kind of complex surfaces, inter surface has to be polished. So what we did, we have done reciprocating motion as well as this kind of circular motion also. to finish the internal surface of the workpiece entirely on the workpiece surface. So these are the three configuration we have tested. And out of that, this first one we found that this is the better one, which gives better surface finish. Okay, so then this is the experimental setup, schematic of the experimental setup. So this finishing zone, you can see here lots of components here. You can see so many components are available in this finishing zone here. Okay, so this is the experimental setup we have developed in our lab here. Uh, uh, so this setup, actually this finishing zone we have developed here. So this is the workpiece here, magnet fixture and workpiece fixture in this zone. So this total assembly, it is rotated by a AC motor over here. It is rotated by a AC motor. And then this kind of reciprocating motion is given by this actual hydraulic unit. And here there is a stirrer is there. The stirrer is used actually for steering action for preparing our this MR fluid here. Okay, so this is the controller here. This controller which is used actually for this hydraulic unit. Okay, so and this motor controller is also there, which is kept here. So another motor controller is also there. Okay, so using this to controller, you can control motor as well as this hydraulic unit, and this total finishing setup actually it is automated. So during finishing, you don't need to, you just have to observe. You don't need to bother any other thing. Okay, so it is an automatic process. So without actually this rotation, we have only this shear stress and magnetic force indentation forces are there. Okay, like in metal cutting operation, there is an indentation depth of cut we give, and after that we give feed force, feeding motion for doing the removal of this material. And in this case also, because of this rotation, our centrifugal force also added along with this magnetic force, and also there is a fluid is flowing, so that's so there is a radial force is also there, and there is a shearing force is also there. So this radial force, magnetic force, and centrifugal force will give indentation into the workpiece, and this tangential force and then shear force will give the shearing action. Will give the shearing action on the workpiece surface. So these abrasive particles you can see here in that polishing media. It comes in a because of this reciprocating motion and as well as the shearing motion. These abrasive particles comes in a helical path. Okay, so it comes in helical path. So entire surface will be polished by this process. Okay, so few other things actually I want to show here. So after developing this setup, we have done experiment on flat workpieces. So we have taken this brass, stainless steel, and ENet. For ENet workpiece, we have found that actually we did not get, as it is a magnetic workpiece, we did not get finishing. So this is the set means Maxwell simulation we have seen. And in case of actually this unit magnetic workpiece, actually this magnetic lines of sorry, this is the magnetic workpiece. So in this case, actually magnetic lines of force. So this is the this column is actually for unit workpiece, magnetic lines of force. It is generating in between this the magnetic workpiece, the unit workpiece, and this is the permanent magnet. Okay, so that's why there is a fluid which is kept inside this cylinder here. This fluid actually it sticks to the surface, workpiece surface, and there is no relative motion in between this polishing media and workpiece surface. So for polishing to take place, actually there is a relative movement is required. Relative movement between this fluid and polishing media and the work is required. Okay. Now, but in case of stainless steel workpiece, this magnetic lines of forces, you can see it is uniform here, so entire surface of the workpiece is polished in this case. Now coming to this other thing, on the workpiece surface, you can see we have taken the SCM images. So first one is the initial workpiece surface, which are actually grinded workpiece. And then this the grinding lay. Here you can see it is kind of clearly visible. And then after finishing by MRFF process without any rotation, so this is the grinding lay and this is the MRFF lay. You can see here easily. This whatever these peaks and valleys, actually it is almost polished. In case of rotational MRFA process, you can see because of this rotational and reciprocating motion, this kind of process patterns are generated over the surface of the workpiece. For brass workpiece also you can see. So in RMF process, we have achieved actually very good surface finish than MRFA process here. So same thing you can see here. These workpieces, this become totally reflective here. Okay, so highly reflective surface on brass and stainless steel workpieces, it is visible here. Okay, so these are scanning AFM images of the same workpiece here. So this is the grinded workpiece. This kind of peaks and valleys are visible here in case of this grinded workpiece. So after MRFA process at a different RPM, you can see here with increasing RPM at 20 RPM, so it is better, and then around 67 RPM, you can see here on the brass surface, it is almost 50 nanometer surface finish we have achieved. And for stainless steel, we achieved actually around 110 nanometer surface finish. So this is the finishing surface roughness plot, initial surface and final surface roughness for stainless steel. Then for brass workpieces, this is the initial surface of the spot, this is the final surface of the spot. Here you can see almost straight line, means it is almost straight line. This surface of the spot is become almost straight line here. Now bearing area curve also, there is a huge improvement in case of bearing area curve. So initial surface of the bearing area curve and final surface for stainless steel. So this is the initial bearing area curve, and then it is the final bearing area curve. And we have checked for cylindrical workpieces also, we have done similar experiments. So these are cylindrical workpieces. For that also we have done. So this is the finished one basically. So we have shown here. So this kind of internal surface of the cylinder also we have polished. You can see this kind of mirror-like surface finish actually we have achieved there. Now some results actually I had to show here. So this is the before finishing. After cutting this one, actually you can see here, and after finishing, this is the internal surface of the workpiece. So you can see here this internal surface, it is machined by boarding operation. So it is prepared by boarding operation. So this kind of undulations are there. These are the generatrix marks over the surface. Okay, so these are the generatrix marks here. So and so this is the FM images of the surface. Now after finishing, you can see here it is almost a straight line here. So we got around 16 nanometer on a stainless steel workpiece, and this kind of process patterns also generated. After this one, actually we have developed another setup. So here I'm just going to just final tool actually I am going to show here. So what we did actually, this kind of tool actually we have developed here. So this is a novel polishing tool which is attached to a milling machine head, and it is polished. So this has this tool actually novel polishing tool which is attached to a milling machine head, and XYZ movement is given actually to polish the entire surface, and the workpiece is actually attached to a fourth axis which is shown earlier also. I have shown workpiece whatever the knee joint which is attached to a fourth axis. Like in lathe machine chuck, so there is a fourth axis is there. Now our polishing tool is made up like at the center we have used the permanent magnet. You can see here NDFEP, neodymium iron boron. This is the permanent magnet we have used. So there are different grades are there up to N52. Okay, so at the surface at this point actually just below the this permanent magnet you can see around 0.6 Tesla magnetic field we have achieved, and this kind of actually mu metal we have used just surrounding the this tool. Okay, so this new metal it is used actually it is used in aerospace industries for shielding the magnetic field, and it will concentrate into a one point. So whatever this effects lines of force going outside, it will not allow to go, and it will put entire magnetic field into this small area. You can see with this configuration, there are different configuration we have set. With this configuration, we have seen that actually this magnetic field actually it is like a spherical one. So along these lines of force, we are expecting these iron particles will form with the chain, say particles will form chain. and this kind of spot contact will be generated in this case. Okay, so using this after developing this kind of setup, so after developing this kind of setup, actually it is attached to the milling machine, and we have tested actually this means using a Gauss meter. Actually, we have measured the magnetic field here in both the process by simulation and also by experimentally where we have measured what is the value at different points, and almost similar magnetic field we have achieved. Okay, so so using this polishing tool, we have tested on the workpiece surface. So so this is the initial surface of the workpiece. Here we have used titanium because we are going to finish titanium workpiece. Okay, so this femoral knee joint, actually we have considered here femoral part of the knee joint, and so this knee joint we have mostly it is used titanium alloy. Okay, so this kind of small workpiece as a prototype for developing our setup. The small workpiece actually initially have started polishing. Then after polishing, you can see this kind of highly polished mirror finish surface we have achieved here in our lab. So this is the surface topography, and this is the surface roughness profile before finishing and after finishing. So highly finished surface around 10 nanometer is achieved here. You can see. Now after that, actually, we have used two different kinds of fluids here. Titanium, we are polishing actually titanium. So in the first type of fluid, we have used actually hydrogen fluoride with the nitric acid. Okay, so and the second type of fluid, actually, we are using hydrogen peroxide. Okay, so as our titanium, it is very hard material with this kind of acid. Actually, we have included, we have added in our polishing media. So here in this table, you can see what kind of composition we have considered here. What composition? So here you can see what kind of composition we have considered here. Okay, so after that, actually, so you can see this is the initial surface, SEM image of the initial surface and SEM image of the final surface here. Then surface roughness profile is by using type 1 fluid. We have seen actually very smooth surface is achieved. Okay, for type 1 fluid, and for type 2 fluid, it is little bit damaged surface. Not damaged, basically it is polished, but not like actually this type 1 fluids. In type 1 fluid, actually, it is more aggressive, so it polished actually very smoothly. For type 2 fluid, actually this finishing efficiency a little bit less because this hydrogen peroxide it is not that much aggressive. Okay, so this type 2 fluid, after that, actually we have used this wettability test for type 1. So initially, so this is for type 1 fluid, and this is for actually type 2 fluid. Okay, so after finishing, so type 1 fluid, we have seen that actually it is hydrophilic, and type 2 fluid actually here in this figure, you can see here it is hydrophobic fluid. So for the hydrophobic surface is generated on the workpiece surface. So after, so this type 2 fluid, it is good for it is good for where actually this like our teeth implant, actually in that case actually lots of muscle growth, all these kind of things are there. So for better osseointegration, actually this type 2 fluid is required. And type 1 fluid actually it is, this type 1 fluid with surface finish with the type 1 fluid, this is required actually in femoral knee joint. They are very smooth surface finish required. So after that, actually, we have seen different kinds of tool path. Actually, we have checked. So this kind of spiral tool path and this kind of parallel tool path or raster design we have checked. Actually, we have found that this raster design actually it is good. Yeah, in this case, actually, the surface finish we have better surface finish is achieved. Okay, so after that, actually, we have done force analysis. How to what kind of forces are actually coming on the tool here or on the workpiece here. Okay, so this is the normal force and shear force. Okay, so this force analysis. So what we did actually in this case, We have used actually dynamometer. Okay, so this kind of dynamometer actually we have kept crystal dynamometer, and above that actually there is a plate, purchase plate is kept, and where workpiece is kept, and this is our polishing tool here. From this actually we from this setup actually we have measured the normal force and shear force we have measured from here, and then actually from simulation we have measured actually what is the spot diameter. So in this case here the spot diameter it is 26.1. Okay, so with the difference gap actually the spot diameter changes. Okay, and now after that actually we have started doing our this experimentation on freeform surface. Okay, so on this freeform surface prosthetic implant we have considered. So this kind of freeform surface, so it is made of actually titanium alloy. It is made by using a 5-axis CNC machine with a with vibration assisted 5-axis CNC machine. So here this is the finishing setup. You can see. This is our Nobel polishing tool here. So there is a shaft over with which actually this on that shaft actually we kept our on that shaft actually we have kept our this knee implant. We have kept our knee implant over there, and then it is using this fourth axis. It is rotated with a very small RPM, around 5 RPM rotation. It is rotated, and then this XY movement, XYZ movement is given through this actually this Z movement is given on this tool, and XY movement is given on the table. Okay, like that actually this entire workpiece actually knee implant actually is polished here. So here you can see this polishing size to spot diameter is around 30 millimeter diameter. So our this polishing spot diameter is around 30 millimeter here. Now in this case actually I have to show one thing. We need to have actually this polishing force would be perpendicular to the workpiece surface. So whatever tool we have used here, you can see we have started from here. So started from at this point. Okay, so every time you can see here actually this polishing tool is perpendicular to the workpiece surface. So what we did actually, we, suppose at this point actually it is rotated, it is polished for a certain time, and this tool it is rotated around its axis. And at the same time, there is a small rotation is given, and small rotation. Then there is a stop. Means we have used dwelling motion actually. Basically, dwelling motion we have given. So it is polished for a certain amount of time, very small amount of time for a certain spot here. When it is polished, then it comes to the next point. And every time it is rotated with this fourth axis, so that every time this tool it should be perpendicular to the workpiece surface. Like that, entire surface of the workpiece is actually polished. So after that, actually a different position with our main requirement is actually nano finishing as well as actually uniform polishing through the entire surface of the workpiece. Okay, so like that, we have polished actually entire surface of the workpiece, and at different surfaces actually we have measured surface finish, initial and final surface, and percentage change in array. And at a different spot, we can see that actually this in the standard deviation also very less. Okay. So these are the surface roughness values we got here. You can see this 60 at different positions, 40 nanometer, 20, 50, and 70 nanometer. So these are the surface topography lot. I'm not going to explain again all this thing. Okay, so this is the knee femoral knee implant after finishing on a titanium workpiece over here. Okay, so after that actually we have done certain performance analysis or wear test. Okay, so for this wear test actually we have used a pin on disc. This is the pin actually which is made of this titanium, and this rotating rotated surface because wherever this new implant is there, just below there is a ultra high molecular weight polymer which is used. It is kept just below the pin, And this workpiece it is rotated. This wheel which is rotated with a certain RPM. Okay, so it makes a scratch marks over the surface. And two types of pin we have considered. Both are actually made of titanium alloy of grade 5. One is actually hand polished, another one is the fluid polished like this one. Okay, so these two pins we have made this kind of scratch test and sorry wear test on a pin on disc, and we have found that with MR full fluid based finishing pin, it removes less surface debris from the workpiece surface. So this is the disc here, ultra molecular weight polymer. Okay. Now, after that, we have done certain amount of actually some work on miniature gear. So this kind of gear, you can see these are the small gears. These are the brass and stainless steel gears we have used. And MRFF setup, the same setup actually we have used for polishing purpose. And this kind of fixture actually we have used here. So this fixture, it contains the workpiece miniature gears, and these gears actually it is made of wire radium. So using wire radium process, actually we have these kind of gears, miniature gears uh, we have actually fabricated. And in that gear, actually this kind of scratch marks or their pits are available. Okay, so unless it is polished properly, so this gears does not work. So how this fluid is coming through this gear, you can see through this fixture. So it passes through this gear and it goes out from this fixture over there, and then so after that, actually these are the stainless steel and different surface, involute surface, top surface, face, different surfaces. We have these are the uh, optical microscope measurement. Okay, so they are the on stainless steel workpiece, and here these are the ACM images. So you can see these are the bars. Whatever these bars are there, it is completely removed here at these finished surfaces. You can see. So in this case also, whatever these bars are there, it is completely removed. Okay, uh, uh, so uh, uh, so I'm completing my lecture here. Okay, so I'm going to conduct one tech-sponsored short-term course on advanced manufacturing technology from December 21st to 25th. So those who are interested, you can contact me. So this is my email ID, manasdas@itg.ac.in. So this is for TechIP map. So this as it is sponsored by TechIP. So they have a limitation actually only TechIP mapped to keep three mapped colleges, these faculty members and research scholar only actually they can take part. Uh, uh, so if you are interested, you may mail me. So this is my email ID, manasdas@itg.ac.in. So thank you. So now if you have any question, you may ask. I shall try to clarify. So any
Any,
questions?
que-
If you,
any questions from the participants? You may please.
sorry, sorry, it is not audible actually. Is it audible?
Yes, sir, your voice is audible.
Okay, okay. So otherwise, if you have any questions, you can mail me also. Uh, so I shall try to clarify all the whatever queries are there. Okay. So otherwise, you may call maybe around 10 minutes are there. So you may ask any questions. I shall try to clarify. Otherwise, you can send me your queries through mail also.
So I'm Shweta, sir, from Department of Aeronautical Engineering. MLR
Okay.
Institute of Technology. So I thank you on the behalf of entire team of the department and the management of the college for taking out your time and giving us a very quick reply actually. I mailed you and you have given me a very quick reply, which I always feel that privilege of having the connections. So thank you very much, sir, for taking out your time. Any questions from the participants, you may please drop in the chat window. I think participants also like they are happy with the session because it's completely a new topic,
Yeah.
and we find only few people working on this nano composites and smart materials, and that too into a very narrow stream. So, so thank you very much, sir.
Okay. Thank you, ma'am, actually, for giving me opportunity